Previously. Can we get a better understanding of what gravity is, assuming mass is a composite of time? By introducing extra time dimensions, this whole gravity equation is going to change. The existence equations account for infinite regression and infinite progression of relative frames of reference using a set of continued fractions. These equations infer multidimensional time and can be transnumerated into a three-dimensional time coordinate system. When these equations are plotted within a multidimensional time construct, it becomes apparent that the slope angle of ordinary linear time and the slope angle of relative time are equivalent, using infinite series of non-inertial frames.
So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first.
So do objects with a significant difference in mass fall at the same speed or not? Assume that from a particular frame of reference, more massive objects fall faster than less massive objects. We can assign this concept to a position frame of reference. However, when an object moves through space, it loses some of its relative time. We can assign this concept to a momentum frame of reference. When superimposed together simultaneously, the heavy and light object both fall, on average, at the same rate. This is an entirely new approach to the equivalence principle. This becomes the place where general relativity and quantum mechanics merge. These four potential relations have a complex conjugate type of relationship. Both masses are experiencing the same acceleration, though not in the same way.
Through an action at a distance, the inclusion principle and the exclusion principle set the perimeters of quantum entanglement, where the inclusion principle represents the probability that all the mass is concentrated into a single point, and the exclusion principle represents the probability that all the mass is separated into distinct points. When two separate masses are in a free fall towards some large third mass, the same principles apply.
How does all this apply to general relativity, the Big Bang, the inflation period at the beginning of the universe, dark matter, and dark energy? Is space-time fragmented, segmented into quantized bits of information, or causal sets, as Faye Dowker suggests?
There's something atomic going on, that the space-time itself is atomic on Planckian scales. So this information about which events in space-time can influence which other events in space-time is altogether called the causal structure of space-time. So these two ideas, that space-time is fundamentally atomic and that causality is its basic structure, something called a causal set.
Or is space-time smooth and continuous with curves, bends, and warps, just as Einstein had predicted?
We observed a gamma ray burst. A gamma ray burst is a huge explosion. That gamma ray burst produced a large number of photons, one of which had enormous energy, very short wavelengths. Those photons traveled 7 billion years to reach us. Because Fermi saw no delay in the arrival time of the two photons, it confirms that space and time is smooth and continuous, as Einstein had predicted. And it shuts the door on several theories of everything that had predicted that space and time might be foamy enough to interfere with light.
Is what we call space-time part of everyday objective reality? Or is it just a mathematical construct that appeals to our perceptions? The answer could be all of the above, depending on our frame of reference. When we apply temporal mechanics to physics, it appears that there are underlying aspects to relativity that subtly show up in quantum mechanics as extra dimensions of time. Obsolete points of view regarding the nature of time and relative frames of reference may be at the center of the mismatch between quantum mechanics and general relativity. There have been great advancements in the understanding of space and its complex multidimensional nature, but not time. Most physics theories tend to have a unique premise in common: one time dimension. In fact, there is a growing consensus that time is just an illusion.
Well, the approach that you're referring to is one that starts with the basic principles of quantum mechanics and applies them to Einstein's equations as best we can without really introducing anything new. And one of the features that emerges is that time does disappear from the equation, so-called Wheeler-DeWitt equation. But in no way would I say that string theory leads us to this particular way of thinking about quantum gravity or the early universe. So I'd say it's really up in the air how these quantum theories that involve gravity deal with time. If you were to ask me what the next major breakthrough would be, I would say it's coming to a firmer understanding of what time is in these theories, where it comes from. Is it fundamental? Is it built up from something more basic? And what does that tell us about the fundamental ingredients of the world? So that, I think, is a big frontier area.
Applying extra dimensions to time can successfully modify modern physics without violating the conservation laws long held to be true. Notions of quantum gravity and curved space-time can successfully be replaced with an infinitude of relative frames of reference, progressing and regressing through infinite series of relations, which imply the existence of multidimensional time. Re-examining the basic expression for acceleration using temporal mechanics, notice that this expression is directly stating that space occurs over a period of time proportional to acceleration. With basic algebra, we can simplify this expression into terms of space. Space itself can be expressed as a specific relationship between temporal coordinates using a four-vector expression. We can simultaneously use a spatially oriented metric and/or a temporally oriented metric for describing physics. Notice that in transformations between spatial and temporal coordinates, the metric does not change sign, it just changes placement. This gives us an ability to translate between outer space-time coordinates into inner space-time coordinates, or vice versa, using intermediating temporal coordinates. Extra time dimensions allow for variances between spatial and temporal coordinates while maintaining both covariance and invariance principles while using Lorentz transformations. This application to relativity becomes a critical insight into the significance of applying temporal mechanics to physics.
In 1619, Kepler published the third and final facet to his own laws of planetary motion. After observing that planetary motion is elliptical and heliocentric, Kepler calculated that the square of the period of the planetary orbit is proportional to the cube of the semi-major axis of that orbit, known as Kepler's third law.
We can derive Kepler's law of planetary motion by setting Newton's gravitation equation equal to Newton's second law. If we consider Kepler's second law firsthand, it states,
A line joining a planet and the sun sweeps out equal areas during equal intervals of time.
though relativity and quantum mechanics were not available to Johannes Kepler, we can revisit Kepler's third law with respect to Lorentz transformations, describing either the homogeneous covariant or unchanged invariant qualities in a physical system. There is a similar principle at play here. In temporal mechanics, Space and periods of time are proportional relative to the passage of time. When applying three-dimensional time to Kepler's third law, the spatial radius can be substituted with a temporal radius. Once substituted, the cube of a temporal radius is proportional to the square of the period. Interestingly, we can view the cube of a temporal radius as a volume of time, or if we apply a negative sign, we get the temporal mechanical definition of mass and/or energy. Further, if we substitute t cubed with mass or energy and square root both sides, we get that the period is proportional to the square of the mass energy, consistent with the physics of a simple harmonic oscillator. Returning to the classical gravitation equation and substituting the temporal radius for the spatial radius, by expressing the Newtonian gravitation equation and Newton's second law in terms of temporal coordinates and setting them equal to one another, we derive a principal concept from temporal dynamics, namely that the passage of time is inversely proportional to the period of time for some given moment. Assume that there is no difference in the passage of time between t double prime and t prime, and that big N and little n equal 1 as a form of local symmetry. Space and gravity have an inverse proportional relationship based on the relationship between big N and little n. This appears to account for the inverse relationship found in the classical gravitation equation, where the relation terms big N and little n partially account for the mass, but where is big G, the gravitational constant? Through various proportions of a variety of relations, the gravitational constant becomes a fixed quotient between varying rates of the passage of time. Therefore, the acceleration term t double prime over t prime will be set to equal big G. This basic expression using temporal coordinates can be applied to other coupling parameters found in physics associated with forces other than gravity, with or without units depending on the application. With these definitions and our new equivalence principle, we can apply temporal mechanics to issues in cosmology. Three-dimensional time offers solutions to the problems of dark energy, dark matter, and an alternative explanation to the inflationary period of expansion right after the Big Bang. Re-examining the Big Bang theory, we must ask, what is it based on? The Doppler effect has been the best explanation for why we see a redshift in distant light as we look further and further into outer space at more distant galaxies. This would suggest that galaxies are moving away from one another, indicating that the universe is expanding. On the other hand, what if light itself becomes redder as it travels over greater and greater distances through space, or due to some kind of unknown physical phenomena? This type of concept, attributed to physicist Fritz Zwicky, became known as tired light and is currently dismissed as a fringe theory. Most variations of tired light theories involve a gradual energy loss by photons as they travel through space as a way to account for the redshift we see in light from distant galaxies. Tired light theories face several problems.
There is no known method for calculating apparent changes in a photon's energy without also changing its momentum.
Since photons have zero rest mass, even though they possess momentum, photons can neither slow down nor speed up. They always move at the speed of light. Therefore, the momentum of a photon cannot change without violating the conservation of energy.
Tired light models do not account for the observed time dilation of high redshift supernova.
Supernova, which are massive star explosions, can be used as standard light signals for measuring distances across the universe. Since supernova only occur within specific energy ranges, like candles, supernova can be compared with one another, and whichever one is dimmer must be farther away. Likewise, by comparing the redshift in light from different supernovae, an accurate measurement of the expansion of the universe can be made. Scientists working on the supernova cosmological project wanted to accurately measure the expansion rate of the universe. When comparing the redshift of the supernova against the redshift of galaxies from where the supernova had originated, as a way of calibrating measurements of the expansion rate of the universe, it became clear that the expansion of the universe was accelerating. By the end of 1998, data concerning the acceleration of the expansion of the universe suggested the existence of a mysterious dark energy which appeared to dominate the universe. Tired light theories never anticipated this unexpected discovery, and some physicists used this discovery to put an end to tired light theories once and for all.
The tired light model cannot easily reproduce the black body spectrum for the cosmic microwave background.
Other discoveries, such as the cosmic microwave background and several of its properties, such as fitting a black body radiation curve, work well with the Big Bang theory and appear as impossibilities for tired light theories to tackle. In a tired light model of the universe, the energy of the cosmic microwave background will diminish, but the density will not decrease to match the energy of a cooler black body. Since the photons would be losing energy and not decreasing their density, the resulting curve would not fit a black body curve and would not match data. However, when the general idea of tired light is examined through expressions in terms of temporal mechanics, it comes back with a vengeance. Consider that the calculation for redshift based on wavelength is as follows. Inversely, the calculation for redshift based on frequency is as follows. Either way, and without modification, the equivalence principle between linear time and relativistic time, derived using three-dimensional time and continued fractions corresponding with infinite series of non-inertial frames, can account for the redshift, indicating that the universe is not necessarily expanding. Alternatively, light could be redshifting on its own, over time, relative to distant observers without losing or gaining any energy. We can apply the basic temporal mechanical definition of mass to light and demonstrate this further. Let's examine a moment of undisturbed travel of a single photon using the simplest expression of a closed, isolated system. The difference between the final mass and the initial mass of the photon while traveling at the speed of light equals 0. Simply put, there is no change in energy or momentum of the photon as it travels, undisturbed for a period of time. The change in the passage of time is inversely proportional to the square of the period. Since there is a change in the period of time for a single photon, the passage of time decreases relative to the observed frequency of the traveling photon, and the photon appears to have increased wavelength. The period of time for a traveling photon increases proportionally with distance. Modifications can be made to this basic expression and, if parameterized precisely, can account for the observed supernova redshift data shown in this diagram provided by the Supernova Cosmology Project. So that the mass of the photon doesn't change in order to maintain the conservation of energy, the passage of time must decrease proportionally as the period of time increases. Since the passage of time decreases as the photon travels through spacetime, the wavelength of the photon becomes longer relative to some observer in a non-relativistic frame of reference, say that of an astronomer billions of light years away. This basic application of temporal mechanics to special relativity affects the concept of simultaneity, Adding extra time dimensions to the parameters of light can account for the redshift observed in light from distant galaxies, bypassing traditional objections to theories of tired light. Therefore, it can be argued that light naturally appears to redshift as it travels undisturbed through empty space without violating the conservation of energy and without a Big Bang. The conceptual point of origin, where space and time appear to have begun, is known as the Big Bang singularity. Here, space-time is reduced to a single point. On the other hand, when viewed through the lens of three-dimensional time, it becomes nothing more than a temporal vanishing point. Just like parallel lines on a road in the middle of nowhere, they appear to converge at the vanishing point, but in reality, they are still parallel lines. Instead of a road that stretches out into the distance, the frequency of light stretches out over a period of time. Though time appears to have a beginning 13.7 billion years ago, that beginning is arguably a temporal illusion, an artifact from limiting time to a single dimension. It could be argued that modern cosmology is a collection of artifacts resulting from limiting time to a single dimension. Ptolemy's ancient geocentric model of the universe used complicated mechanisms known as epicycles to explain the bizarre retrograde motion of the planets. Later, Copernicus noticed that this apparent retrograde motion was actually an artifact in our perspective due to our Earth-based vantage point. Once the imagination of Copernicus was able to see outside the geocentric model, what appeared to be bizarre retrograde motion was nothing more than uniform circular motion that did not need complicated mechanisms, such as epicycles, to explain the retrograde away. Similarly, the current cosmological model of the universe, which has only one time dimension commencing with the Big Bang, needs mysterious dark matter to hold it together and consists primarily of some mysterious dark energy, which inexplicably is accelerating the universe apart. Are these just modern-day versions of epicycles? Applying three dimensions of time and temporal mechanics to astronomy and cosmology can be used to show the universe is not necessarily expanding and that dark matter and dark energy are actually artifacts of applying only one dimension of time to physics. If we apply the new equivalence principle to dark matter and dark energy, it becomes apparent that when we look at extremely distant objects, or when we look at extremely massive objects such as galaxies, we're not only looking at three dimensions of space, we are also seeing three-dimensional time. Though tired light theories have been reserved for crackpots, that the theory's originator Fritz Zwicky also conceived dark matter lends to its re-examination. Let's assume that light decays, say, after 13.7 billion years. In this case, the evenness of the cosmic microwave background might suggest that the universe, as far as light is concerned, is immeasurable. The diffuse extragalactic background radiation may act like an idealized blackbody, acting like a cosmic permeable membrane, absorbing and emitting radiation of various wavelengths from within and from without our universal light cone of 13.7 billion years. Some of the light, radiation, and luminous objects existing within the measurable universe may actually be mutually exclusive, having different origins. The universe itself may be much, much older than it appears. Some galaxies may be older, and some stars may be much younger. Regardless, our ability to measure and fathom the cosmos may be limited within a horizon of 13.7 billion light-years. It could be suggested that photons redshift so much after 13.7 billion years, they approach violating the conservation of energy, needing additional momentum to continue propagating at the speed of light, implying some sort of wavelength or frequency limit corresponding with the decay modes of photons. Hypothetically, since the speed of light equals wavelength times frequency, and the frequency decreases as the wavelength increases to 13.7 billion light years, the frequency cannot get any lower without the photon violating the conservation of energy by either disappearing outside the observable universe or converting the photon momentum into rest mass. As a way around this dilemma, the photon could couple with some other photon in a similar situation and oscillate into becoming mass-bearing particles. As the photon pair approaches coming to rest, the photons first couple, then decay into mesons or pions, which then decay into being extragalactic radiation. Rather than there being an inflationary period after the Big Bang, this would suggest a deflationary period where electromagnetic radiation begins to break down 13.7 billion light years away from an emission source. A cosmic horizon could act like an idealized blackbody, where absorptivity and emissivity are equivalent and the temporal vantage point of the universe has a ratio of 1. This would support the idea that the universe has a flat geometry, preserving the Pythagorean theorem as a universal truth. However, this revised higher light theory has a major weakness. How do we get from long wavelength with low temperature, with high redshift, to light with a short wavelength or high energy photons, such as in the Primakov effect? Tired light is exactly that, tired, redshifted, dragged out, whereas gamma rays that could couple and decay into mass-bearing particles are high energy, excited, not low frequency infrared. So how can redshifted photons couple, let alone have enough energy to decay into particles with mass? This is where three-dimensional time unveils its most bizarre impact on physics, cross-conjugation, also known as cross-symmetry. Space can be expressed in terms of temporal coordinates. Mass, spin, and charge can also be expressed in terms of temporal coordinates. As a result, an unexpected symmetry emerges. When applying three-dimensional time to physics, shocking consequences turn the inflationary period after the Big Bang inside out.
Science blogs are buzzing over a new experiment, one that leaves most laymen scratching their heads. The study in the journal Science claims to have created an atomic gas with negative absolute temperature, meaning a negative number on the Kelvin scale. Hold on, how does something get colder than the coldest possible state? If you're like most high school science students, you were probably taught that absolute temperature is the measure of how much atoms vibrate. As you get colder and colder, they vibrate less and less until they come to a standstill at absolute zero. But science writers trying to explain the latest experiment say that's not quite the whole story. A more accurate description of temperature would represent a loop. Anything beyond absolute zero or infinite temperature would be in the negative. Hopefully that gets the point across. Negative doesn't mean below zero, it means the opposite of positive. It's basically a different state of matter, a kind of hot-cold.
Certain gases condensate at supercool temperatures and can form superliquids. When particular gases or conducting materials are supercooled to extremely low temperatures, they begin to exhibit peculiar behavior.
Helium is a remarkable substance. It has two different and easily distinguishable liquid phases, a warmer and a colder one. The warmer phase is called liquid helium-1, and the colder phase, liquid helium-2. The two phases are separated by a transition temperature, known as the lambda point. Helium boils at 4.2 degrees Kelvin, and the lambda point lies at roughly 2.2 degrees. As cooling progresses below 4.2 degrees, the specific heat of liquid helium rises astonishingly as we approach 2.17 degrees, the lambda point. As we approach 2.17 degrees, boiling becomes increasingly violent. Suddenly it stops. This was the transition. The liquid you now see is helium-2. Even though evaporation does continue, there is no boiling. This phase acts as if it had a large heat conductivity. The specific heat of liquid helium is very large at the lambda point. In fact, it behaves abnormally even below the lambda point and falls again very rapidly with the temperature. This discontinuity in specific heat is another reflection of the fact that we are dealing with a change in the phase of the substance. A small piece of cotton is stuffed into the constriction between the tube and the bulb, and the bulb has been tightly packed with one of the finest powders available. This powder presents extremely fine capillary channels. The liquid helium is below the lambda point. We submerge the bulb, and then we'll send a beam of light from this lamp to a point near the top. It focuses some heat in the form of infrared radiation on the point in question. Liquid helium flows through the hole in the bottom of the bulb, through the fine powder, and rises above the level of liquid helium outside. The superfluid flows spontaneously from A to B, from a cooler to a warmer place. Point A is in the cold liquid, but B is being heated with infrared rays. The second law of thermodynamics positively says that heat cannot of itself flow from a point of lower to a point of higher temperature. What does this mean to us here, knowing as we do that the superfluid is flowing from a colder to a warmer spot? Any internal energy it may still possess is no longer thermally available. To say it precisely, it has zero entropy.
In superconductors, when the temperature is low enough, electrons can form Cooper pairs where the electronic and nuclear spin states couple together, a behavior typically forbidden in all other temperature ranges.
In most cases, liquid helium is required as a cold bath to produce superconductivity. First, we want to cool the sample of tin wire. So, at 4.2 degrees Kelvin, tin is a normal conductor. The transition temperatures between the normally conducting and the superconducting phases lie close to the absolute zero. The liquid helium has been cooled below the transition temperature of tin at 1.6 degrees Kelvin. As you can see, the resistance has dropped to zero within the limits of accuracy of this instrument. The voltage across it is zero. Their electrical resistance suddenly drops in value at the transition temperature. Superconductivity is a state of zero electrical resistance, or, to put it the other way around, of infinite conductivity. Although this is remarkable enough by itself, superconductivity is quite a bit more than that. The external magnetic field influences the temperature at which this transition occurs. A small bar magnet is brought down toward a lead cup whose temperature is 4.2 degrees Kelvin. Even in the field of the magnet, the bowl remains superconducting at 4.2 degrees. And, by Lenz's law, the magnet is repelled. In the normally conducting state of a metal, the conduction electrons behave like free particles. In the superconducting state of a metal, the electrons become bound as pairs. It is shown that the most likely pair to form is that one in which the paired electrons have opposite spin. This line of reasoning makes the pairing of electrons a plausible model for superconductivity.
The consistency of applying temporal mechanics to conventional physics is most apparent when applying three-dimensional time to thermodynamics. The relationship between temperature and mass becomes more apparent. The rate of the passage of time is synonymous with temperature, whereas with mass, the passage of time is associated with density. An increased temperature tantamount to an increased mass is an increased rate of the passage of time. The dynamics of entropy, in terms of temporal mechanics, lends itself to the theory of gravity. In temporal mechanics, the concept of the passage of time applies to moments, temperature, and energy. The reversibility of the passage of time provides temporal mechanics extra degrees of freedom unavailable to conventional physics. As a result, new forms of symmetry arise. If we approximate for simplification, we see that this dilemma is an example of an identity crisis. Relative to the traveling photon, it does not redshift, but relative to some observer, the photon is redshifted. Since distance is proportional to the square of the period of time, and since period is inversely proportional to the same, the observer and the traveling photon are not sharing the same temporal frame of reference. Therefore, by applying the basic existence equations to this issue and using a centered frame of reference, we find that as the photon relative to the observer is redshifted, the observer relative to the photon is blue-shifted. The interactions are no longer simultaneous in linear time. There are two concurrent timelines running side by side, but staggered. The timeline relative to the photon is further in the future relative to the observer, and the observer is further in the past relative to the photon. Therefore, the relation between the observer and the photon occurs in two separate timelines, not one. In this example, both the observer and the photon have temporal frames of reference that correspond together through an inversely proportional relationship. Frequency and wavelength have a reciprocal relationship. Applying this concept to the interaction between the gamma frame of reference and the infrared frame of reference could be categorized as a modification to Kirchhoff's law. By simply applying the inversely proportional relationship between frequency and wavelength to temperature and applying it to Kirchhoff's law, we get an equivalence that allows for the proposed decay process of tired light. The photons couple together, forming an identity crisis. The wave functions for both photons turn into a superposition of states fluctuating between identical and distinct states. The increased probability density and temporal potential form a wave function echoing high-energy gamma rays. Once this state has enough potential, this state is unstable and immediately decays into a neutral meson, then radiates. The energy that disappears from the infrared frame of reference is the energy that materializes in the gamma frame of reference. In actuality, the conservation of energy is not broken, there is just a new symmetry.
For instance, a gas at positive temperatures will always have more atoms at a low energy state, with fewer and fewer at higher states. Negative temperature is just the opposite. Lots of particles at the highest temperature, fewer and fewer at lower energy. The experiment opens up some bizarre possibilities because matter at negative temperatures has some really weird behaviors. One could create heat engines, such as combustion engines, with an efficiency of more than 100%. The engine could not only absorb energy from the hotter medium, but from the colder medium as well. Studying negative temperatures could also help scientists better understand other strange behaviors in the universe. And Live Science says it could also help shed light on dark energy, which shares some of the characteristics of negative temperature gas. Nature adds some negative gases could even defy gravity, moving away instead of being pulled. Don't ask us to explain it.
Of all the major issues facing cosmology, there is still one we have yet to touch upon.
Seth, maybe you have another question in the meantime?
Do you think there are stars and galaxies made entirely out of antimatter? And if yes, then do you believe we can identify them? That was from Twitter.
In fact, we have no evidence for that yet.
This really gets right to the heart of a big question we have. Antimatter is just like matter. All the interactions we draw are the same, except for the opposite, for the minus signs. Everything looks symmetric in our world for matter and antimatter. Most of our theories have a lot of symmetry. One would expect that when there was a Big Bang, 13.7 billion years ago, that there was an equal amount. And if that was the case, then probably we wouldn't be here, because probably by now we would have collided. Everything would have collided. Most of the material seems to have disappeared but we're left. We're the sort of dust that remains, and it looks like we're just matter, because we don't see these high energy gamma rays coming from different places in the universe where you would have collisions, where you would have the matter and the antimatter coming together. And there are experiments looking for that. In fact, there's an experiment on the International Space Station called AMS. It's one of the experiments is actually looking for these gamma rays and not seeing it. So that's a huge question. Where did it go? Where's the antimatter?
The fact that when the universe was a minute old, there was a tiny difference in the amount of matter and antimatter present there. I mean, really, really tiny. No more than 1 part in a billion. And that's what we're trying to understand with LHCb. And quite clearly, if we have half matter and antimatter to start with, and we now have matter today, they must behave differently in order to reach that state. We don't really understand this effect, but we want to understand it. It is the reason why the universe looks as it does to us. It's a very important unanswered question in physics and particle physics and astrophysics all over the place.
If we look at the high redshift supernova chart again, we can see one of the curves corresponds with omega for mass and omega for the cosmological constant, whereby 25% of the universe would be composed of matter and dark matter, then the remaining 75% of the universe would be composed of dark energy. There have been more precise measurements indicating that the universe is composed of approximately 72% dark energy, 23% dark matter, and 4.6% atoms. Applying the basic existence equations to the proportions omega 0.25 and omega 0.75, corresponding with the idealized curve plotted with high redshift supernova, we get the following results. From this, we could approximate that the known universe consists of 71 to 73% dark energy, 24% dark matter, and 3 to 4.6% hydrogen, helium, and everything else. We must wait for more accurate results in order to calibrate these approximations. However, if we take the integral of the value that corresponds to the variation between relative frames of reference, we find that 1/2 x squared, when x equals 3, approximately equals the percentage of visible matter as has been measured. We find the same relationship in classical physics between kinetic and potential energy. This relationship is also found in the Standard Model between the constituents of the first generation of matter particles, specifically up and down quark. Since x squared could be either 3 squared or negative 3 squared, we are left with the possibility that half the visible matter is actually antiparticles. How can this be, given that these antiparticles are supposed to be missing? Where are they? Well, apparently, right here. Everywhere, but going backwards in time relative to the rest of matter. So in theory, matter is made up of particles and antiparticles. Forward-moving particles with reverse-moving antiparticles. But matter itself is stuck in the present between future and past events, oscillating amid forward and reverse time. Matter, then, is composed of particles and antiparticles as an alternating standing wave or a superposition within a time loop. Cross-conjugation uses three-dimensional time loops where half the cycle is in forward time and the other half is in reverse time. After a complete cycle, though a moment of time may have passed in a forward direction, the time loop is conserved. Besides the characteristics of mass and energy, these loops take on the additional characteristics of charge and spin. Using temporal mechanics, cross-conjugation unveils an innovative form of symmetry that appears to be showing up in new physics experiments through a variety of newfangled anomalies. So matter exists, composed of particles and antiparticles oscillating out of phase in opposite time directions. Antimatter, then, would be composed of particles and antiparticles oscillating in phase in the same time direction, which would not be stable, as these particles would annihilate each other upon contact. This concept accounts for the missing antimatter quite well, and is very compelling absent any better explanation. We are now fully prepared to examine the mechanism of cross-conjugation and how it corresponds with both general relativity and quantum mechanics.